Greetings, my friends. This is Dr. Mohamed Nezami coming to you from Jarrah, Jordan. Welcome back to the eighth part in my series on KK and KU band antenna LNB feed structure designs. Okay, now if you just happen to watch this video, this is my YouTube channel. I would urge you to go to the visit this, and you can, by the way, scan this QR code and go to this page here. Um, Basically, I have these parts, seven, six, and so on, and fifth, and so on. All these parts are now um, broadcasting from my YouTube channel. Uh, so I urge you to visit these. Um, Last video, we discussed one of the LNB feed structures. We took as an example KU band one, and we detailed that. So, and this part here, part eight, we're gonna further pursue more example of this. Before we get to that, just in case if you don't know who I am, I'm a freelance RF and microwave designer operating from Jarrah, Jordan, with many years experience in the U.S. and some Asian countries and Middle East. Um, I operate independently, designing remotely out of boards from DC to 35 gigahertz. If you would like to utilize my expertise, please don't hesitate to email me on this. Um, my first few hours are always free consultation. I sit with you, I see what you have. I primarily a lot of my work projects were boards that are in the United States and Europe that needs to be upgraded, where parts are becoming obsolete. I go in and with minimum um, rework, I can update the board with new layout and so on. If it's a new design, I sit down with you and I work with you from specifications to from concept to specifications to system modeling to actual realization of circuits in CAD systems such as Cadence. Okay, I utilize HFSS, ANSYS, Pathwave, System View, and ADS, Momentum, AutoPro, and some other packages as well. In addition to the layout and schematics, I utilize Cadence. So please don't hesitate to reach out to me. I operate very cheaply. Many of these boards that I worked, the cost is anywhere from as low as $3,000, which is, of course, very beneficial to you in the United States. For those of you who are in the United States, I'm a U.S. citizen also. So as far as taxes and it's as if you're hiring a consultant in the USA. So I handle that very easily. Okay, another thing that I'm doing this training. I do this twice a year. The next coming one is going to be hopefully uh, April 22 to 29. The cost of the training is $2,000, and it's a whole week of basically exercising the designs that are here in my website, in my YouTube channel. So you can see anywhere from low noise amplifier for SATCOMs to 5G systems to waveguide antennas, expand radar antennas, um, filters, passive devices, antenna arrays, antenna feed systems, LNA, um, magnetic device technology, arrays for 5G systems, LNBs, box, and so forth, and some passive devices as well. And so you can see a whole variety of stuff on my YouTube channel. So please reach out to me if you like to. You can email me. Basically, the cost is $2,000. You pay for your tickets. I handle everything on this side, picking you up from the airport and reserving in one of the hotels. And as an example, there's a hotel near me, which is this here. You can check this hotel. And you, of course, you get to see the ancient city of Jerash. Okay, so let's get back to the series that I'm doing. So what I have been doing, and this is the eighth part, like I said, is the design of the interaction between the LNB and the horn antenna for any of these systems, SATCOM on the move to large gateways and deep space probes, ground stations to VSATs, direct TV, KU band, and so on. So I have dealt with in you can go back to my website to my YouTube channel, and you can basically, if you come in here to this let's see, a playlist in here, and in the playlist you get this one here, and so far we are, oh,
Hello, my dear friends.
oh,
This
I
is
don't want to
Dr.
play that. Okay, so you can see that I've got all these parts that are in this series, and you can view them um, on your time. I hope you benefit from them. Okay, so the techniques I have been doing is also applicable to the antenna in a package AIP. As you can see, I grabbed some figures from IEEE publications, and you can see that it's very easy to utilize all these expertise that I've done for basically from horn antenna to the LNB and LNB to the board inside. All of that stuff can be utilized as well, as you can see in these examples. So in the coming future session, I'm gonna repeat the same series, except this time I'm gonna do it like I said for antenna in a package, where basically we have an RF chip that we need to mount on the same board in a module where it shares the antennas, and or if it's a flip array package like this, where we have the grid balls in here, and then how to basically manipulate the transmit and receive signals from within the substrate that is either in the module and also in the main board as well. Okay. So basically, where you have the antennas and the same thing, and this applies to like the LEO satellite ground terminals for broadband internet services as well from SpaceX and from Amazon. All right. Like I said in the past years, primarily all of the stuff that I've been talking about uses either circular waveguide or not a rectangle, well, a rectangular waveguide where the width is equal to the height, okay, which is a square waveguide, okay? So both of these ones. And the modes in here are the indicated modes, and you can refer back to the basic theory that I did back in the earlier sections. So I have covered all the five methodologies or styles of the LNB to antenna architecture, and all of these are covered in these parts. Today, I'm going to cover this one here, which is where you have a circular polarized signal propagating picked up from a horn and goes down to an LNB, and we're going to use a mix of printed and wire pan probes to pick the signal, and with minimal loss um, transfer this signal into the active low noise block down converter. Okay, so last time, this is as an example. This is, I picked up these. So we covered this one here. where we it utilizes two of these probes that it picks up. One here where the circular waveguide comes behind, and you can pick the vertical one in here, and then the horizontal one, or vice versa. You could do that as well. Is basically picked up from an aperture of a rectangular waveguide. And the way this one is done, basically, we have a circular waveguide that has a transition from circular waveguide to a rectangular waveguide after you have picked up one of the linear polarizations. We covered this one where we had a septum and a circular waveguide and dual printed probes. We covered this. And then we covered also last section, we covered this one here where we pick up from the circular waveguide, we pick up, as you can see here with the soldering bulb and the soldering bulb, this one goes to the horizontal and this one goes to the vertical, okay? We did cover that. And we covered this one, okay? And so basically, today, actually, this is not right here. I should have put this here, meaning that this is done. This is what we're going to cover today. Is basically one that has a printed probe as well as you can see here. I don't know if you see it. I'll show it to you in a minute. Closer look, where we can see the solder bulb in here that has a pen that goes down and it gets 90-degree bent to pick up the other polarization. Okay. And in pursuit of all of these parts, I had to start out with ANSYS design tools from basically designing a small section of a circle waveguide and a small section of a square waveguide, and then move all the way until where we are today. So you can see all of these, the progression of the development of these is actually in these parts in here. If you go back to my channel, and you will find them in all of these parts. Okay, so they're here, so you can see all of these. Now, if you come to my training, of course, you get all the source files for all these designs, and we go through them. We design them hands-on. Okay, so let's pick today. Like I said last time, let's go back to last time. Last time we covered this here, and this was the um, the one that uses two printed, I mean, sorry, two pens, one that penetrates down into the waveguide to pick up the vertical, and one goes off the side, and then it has a 90-degree bend to pick up the horizontal component. And in the middle, of course, I had a metallic rod that acts as a backshort for the vertical polarization. So the signal comes in here, gets picked up by the vertical pen in here, probe, and then if anything leaks past that, it gets reflected back, and this is a quarter wavelength, of course, and we get, well, once it goes quarter 90-degree and 90-degree, it's 180-degree in phase, and it sums up. Now, while this, the horizontal polarized signal, it doesn't get impacted by this metal pole, so it goes down and it gets picked up by this horizontal pin in here. And then if anything, again, this one is a back short and the waveguide in here. If it picks up anything, if anything passes through, it will come back, and both gets pulled up to the board where I had a via transition from that takes the basically implemented via implemented coax section in the stack layer itself, where I had a circular array of ground vias to implement the outer shield, and then the center conductor is actually this guy here that picks up the signal, and then we go out and of course I have a microstrip line that goes this way and we pick up the signal in here for analysis. And I have done this, and we showed that this thing works, and we have nice isolation, cross polarization, and of course return loss is assured, and and so on. So, but we're done with that. And of course, that is basically this one here. Okay. This is this type here where we have this is a solar bulb in here that goes in the middle of the waveguide and picks up the vertical. And of course, these are two active misfit devices, gas fit devices that pick up the signal and with a very little noise figure. In this case, it's KU band, so it's these have about zero point 0.5 dB. Once it's implemented with all the input and output matching, you get about a half dB of noise figure. And then we go into this basically image rejection filter and onto the mimic chip that then converts the signal and then routes it to the IF. Now, the other polarization gets picked up basically right here. And right here, as you can see, it's on the side of the waveguide because it's exactly like it's implemented in here. I'll show you in here. So we have the other one is off on the side in here. Okay, let me turn my aluminum on so that we can see the outer shield of the show an active device. Okay. Okay, so we have the this is okay. Let's look this way. So as you can see, this is the other probe, and we're implementing exactly a coaxial line with this metal here, where the inner conductor. And I've showed both air filled and with Teflon material filled. So that's on the side in here. That's what you see in here, basically, this guy in here. And he goes through the whole exact processing that you would for the other polarization. Of course, if you look underneath it, underneath the board, you get here's the pan is 90-degree bent, and this is this one in here, which straight down. And all of this is basically going into the circular waveguide. Okay, so this would be the top, this would be the bottom of the board. Okay, so pictorially, we showed that what we have really is we have a horn, corrugated horn in this case, and then we have, as you can see here, as I showed last time, we have two probes, one for the vertical, one for the horizontal, and the middle metallic post. And that's schematically, that's how we draw it basically. We have the vertical pole pickup pin, and then a quarter wavelength away from that, we have the metallic post, which is this one that acts as a short reflection, a back end shorted for the wave for this particular polarization, but at the same time for horizontal, it's transparent. So, and then we have another one here which goes into the page like that. That's the horizontal pin, and this one again has another short back end short, and all of these, of course, is quarter wavelength. And we showed the theory behind that, how that is done. Okay, so just to remind you that whether we are talking about a circular waveguide or a square waveguide with A equal B, of course, we have these two equations that basically governs the cutoff frequency for both waveguides. And then, of course, the macrostrip line is basically it doesn't have a cutoff frequency, so it picks up you can pass DC through it. But the characteristic impedance is given by this, okay? And so, in addition to this, we have the coaxial line equations in here because you got to design this coaxial line yourself. This is not off the shelf. I mean, you're putting in an inner pin in here, and then there's the housing itself, the aluminum housing. Has a tube where this one goes in, and you can insulate that with it via a dielectric Teflon material insulator. And so the characteristic impedance is governed by this, and the cutoff frequency is governed by this, which just proportional to the material inside and the ratio of both diameters of the inner conductor and the outer conductor. Okay, and in addition to that, so we basically So that covers the equations that governs the circle we've got, the coaxial we've got, and then we've got two things, which is we covered also the macrostrip line, but there's also this piece in here. That's the transition that basically takes the signal from the from the probe to the board. Of course, the bottom is all ground on the PCB with a little clearing hole in there, as you can see here. So um, I'm sorry, this one here, as you can see it right there, right there. You can see it. Okay, we can see the little piece of microstrip. Okay, so this has to be designed as well, based on this equation in here, of course. We have an equation that you can basically, and I did on my site, you can go back to one of my videos actually in here. I did cover the transition between the design of via transition in these parts in here. Okay, these are crossovers, but in there I had to go through the design of a transition via transition implemented as a coaxial waveguide. So basically what we have is we put a circular array of vias in here that are ground vias, and then we have the interconductor, and both of course the diameter of between the ground vias and between and the diameter of the interconductor itself, that really is a coaxial line as we implemented here. And you can actually design this so you have the giving what the diameter of the wire that you're going to use as a probe, and then you can come out with the radius where these vias has to be laid out. Okay. All right. Of course, the placement of the probes, as you can see in here, the placement of these probes along the side, the waveguide. Okay, we have the signal goes basically in here, as you can see here. If you go, this is where we the source of the signal. Okay, and then so the placement of these probes relative to each other is really very easily done with the visualization of the mode of propagation that you're working with. In this case, is TM11 in the circle waveguide and TE10 in the rectangle waveguide. And basically, what we have to do really is if you're shorting this end, you would have to go away from this end by a quarter wavelength, and that coincides with the maximum E field. And of course, for the waveguide itself, you really have to go in the middle of the waveguide. Okay. And of course, that has to do with if you visualize the wave inside the waveguide and how it goes from min and max, well, max to max with a 180-degree phase shift. That's how you would have to do that. Okay. And I did cover this in the back slides. So pictorially, what we have to do is we have to place the probe in the middle and then quarter wavelength waveguide length away from the back short. And the back short in this case, it's really both. Because we have two propagating modes in here. We have the vertical and horizontal. So therefore, if you look, there is, okay, signals coming in here. There's the vertical probe in here, and this is the back end short. So this distance from here to here is quarter wavelength. Well, a quarter wavelength theoretically, but we really have to adjust it because of various reasons that are you can see in my that I covered in my earlier videos. And the same way for, of course, this probe here that picks up a horizontal, he's quarter wavelength away from here. Okay. And now the distance between, of course, this and this really is irrelevant. You can move this anywhere you want. Okay. Because this one here, as long as, so these are operating independently. So you can come in on the line of propagation of the along the waveguide propagating signal, and you can place, as long as you place these together a quarter wavelength away from each other, and then this one from the back short here, you can move this anywhere you want flexibly. Okay. All right, so that's basically, and the reason quarter wavelength, we did cover that if you look at the transmission line equation, in this case, if you have a quarter wavelength section shorted, you all know that the quarter wavelength transformer transforms the short to open, basically, and that's what we want. We want the probe in here not to feel any perturbation of loading on the impedance on this side here, okay? All right, so let's get to today's devices. So in this device in here, this one in here, we're gonna close this, and so basically we're done with this. So what we're gonna do is now go to this type in here, which is basically, that's one where we have one of the probes, the vertical probe is printed, while the other one is really a pen, a wire pen. Okay, and as you can see in here, you can see the center pen, and you can see here's the insulator is still attached when this board was pulled out of the housing. So we're going to cover this type here, and to do that, I had to modify this, the other design, and now we're talking this way. And let me just quickly, so this is what we had to do. I had to do. So I had the board in here as the circle we got, and the board now is actually on the other side. It's perpendicular to the waveguide. And the other one in here, that's one of the trade-offs. So there's the differences of this. This one here, the board really is in parallel to the waveguide. So you can, in a lot of times in this case, that's why this one is preferable. And if we go back to these examples in here, you can see that there are many trade-offs between these from a mechanical point of view. This one here is the one where the board is alongside the waveguide, so you can actually becomes a slimmer than this type here, or this type, or this type, because these three here, the board is a perpendicular place to the waveguide, where this one is in parallel. Okay. And that's basically essentially what I have, what this design is here. And what this one does is basically we have a probe in here, okay? A probe in here picking up the horizontal, while the vertical is exactly has a 90-degree, the horizontal is picking up the wave in here, okay? Through a 90-degree bend, okay? So I get this and I come up to the top, and again I implemented a via type coaxial transition from the coaxial line to the microstrip line that is in here. So that's picking up this one, and then of course the other polarization is picked up in here, okay? And of course I have the back end short in this case is this one in here, okay? That's basically is the back short for this one here, this polarization, okay? But what about, okay, the signal is coming from this side. Let me just show you that. Okay, so we're coming in from this side in here. We're propagating down the waveguide. First thing is we pick up this here, and let me show you. Okay. Let's just go to the inner. Okay, this is aluminum. Oh, this is copper. Okay. So we're going to go into just so that I can detail this for you. Okay, so we've got the inner pin is coming in here and getting pin and going up to the microstrip line in here. Now, this one here, okay, you can see that the this one here has nothing to do with it because this one here really is the okay, let's see. What I'm trying to do is let me okay, there it goes. Okay, so I have this in here and this in here. Oh, this in here and this one in here. Okay, so you can see that the what I did, the short pole that was in the other design. Let's go back to the other one. This short pole in here now is implemented using a printed line, and that is basically shown. I'll show you. Let's go. Is right here. So what I had is I had the board itself has a printed on the back and on top a strip of line that basically acts as a back short for this polarization in here. Okay, while the other one, the other probe that is here, that's that guy right there. Okay, okay, vertical. See, vertical and the vertical. Okay, you can see that this guy in here, which picks up the other polarization, okay, this here, this cap acts as a back short to it. So what I did in this one, let me, maybe I should just basically uh, do this so I can show it. So this cap in here is a lid basically that acts as a backshore to the other probe that is in here, and you can see how I made the there is a rat hole in here that basically covers that let the other polarization come out of the board onto the port in here. Okay, while the other polarization is basically done this way. And that basically really implements this type in here. So let's look at some of these and show you, explain and in correspondence to the model that I did in the ANSYS. So we've got a printed probe in here that goes into three-stage LNA in here, you can see. And then I've got another one, which is this guy here. Okay, now there is a lid that covers this. That lid here becomes the back short for this. Okay, and I'm sorry, the other way around. That lid becomes a cover short for this one here. No, for this one, I apologize. What back short for this is basically this here. Okay, and this here, this is the top. On the back of that there is it's really covered with copper, and it's shorted because you can see the vias to ground in here. Okay, and you can see it here. You can see just barely here is the other polarization which comes in here. That's a pin that is bent, and there's this here, this bridge here in the board that has on the other side metallic copper grounded, and that basically acts as a short back for that one, where the cover in here acts as short for this one. And this one, the same thing, has a three-stage amplification as well. Okay, so let's show here again. This is an intact LNB using the same technique. So we've got this sort of bulb in here. That's basically the pin that goes into the page and then 90-degree bent, and then it becomes in parallel with this here, and this on the other side, it's metal, it's printed, it has copper artwork on it, and acts as a short back end to this pole in here. At the same time, say, the other pole is right here, and the cap that comes and covers this, and I'll show you in a second a picture of that, that acts as a short back end for this one in here. And of course, both of them has a low noise amplifier, and then they come in this particular design, they have a single stage of amplification for either one of them. And then they come in and join each other and then go combined into another LNA, and then into a hairpin filter, and then onto a mixer actually, okay? Now, here's another picture that shows it more clearly. So this here, this is the back of it. You can see the back of this strip in here, this strip in here. You can see the back, how the metal is actually, there is a copper ground on it. And then this one is the pen, and you can see it because it's parallel, it's actually looking at you, facing. And this is the cap that acts as a short back end for this guy here. Okay? Another one, just to show you, another example. So here's one, okay, where you can see here's one of the poles. This is here, and it goes into this LNA in here. And then the other one is actually right here. And it goes in, and here it is. You can see the 90-degree bent probe, and this is the metallic printed back end short for this guy in here, okay? And this happens to have two LNBs. This has, okay, so it has one in here and one in here. It's a dual LNB in one board, but they're both implemented exactly the same. So this is the bottom of the board, this is the top of the board. So you can see the probes that pick up the other polarizations right here with a 90-degree bend. And this is the short post that actually acts as a short back end for these probes, this probe and this probe. Okay, so let's get back to the example. What I did is I designed one using exactly the same approach, and I'm going to show you various views of this. And then this is the board, actually. Okay, and in the middle of the board, this is what's implementing the short back end for this guy in here. There's a you can see it right here. This 90-degree bent here probe that goes to the board. This here, this metal is basically the back end short for this guy here, while the cap in here, the extension of the waveguide, becomes for the short for the other one. And of course, I've got the other pole in here. And then this one here is designed exactly like a microstrip antenna. So I got a 50 ohm feed line. I've got a higher impedance line in here section that is for matching. This is quarter wavelength matching the probe in here. So another view of this, another view. And then of course for this particular design, I'll show you in a minute the response. So let's go back to how it's implemented. So let me first go to this guy here and get some transparency so we can see underneath him. Okay, so this is basically the design. So this is, okay, so the signal comes from here, gets picked up by this guy in here, this probe in here, and gets propagated through this coax section all the way to the top and goes into this transition that you go to the side via microstrip line. Likewise, for the other polarization is actually picked by this probe in here, and this here, this cap lid, this cap here, the lid here that is exactly the same size as the circular waveguide has a quarter wavelength section that basically covers the for the back short. So again, just to look at it, here's the center pin. Here's the coax line for one of the polarization, and then the other one. Okay. So let's look at it. You can see it here, okay? And then, of course, the other one is on the other side is right here, okay? And so let's see what else I did. Of course, the short for the short back and short is implemented this. You can see that the board is not hollowed in here. Some of them, they hollow the board, okay, like these ones in here that I showed a minute ago. Like these ones in here, they hollow the board. They cut out these pieces. In my case, I didn't hollow it, so I made it continuous. I kept the substrate in there, for mechanical rigidity. So all I did is I printed this, and a lot of times some people they don't print it on the other side. They just print basically ground on one side, which is the back side where this is a quarter wavelength. So, but what I did is I said to myself, no, let's just put that one, and I stitched it with vias spaced about a half um, millimeter. Now, these vias in here are very important. The location and spacing of these, they act exactly like a substrate integrated waveguide. So you really have to design them with the idea in mind that they have to present a cutoff frequency that is uh, way above the operating frequency. Okay, so let's look at the response of this. So this is my return loss. Okay, so I'm looking at the common port law. This is so this is acceptable, and this is of course got about only a half dB loss, total loss, anywhere from marker one, which is at 9.9 gigahertz, to M2 in this case, which is 12.2 gigahertz. So I could optimize this further, and the isolation is pretty good on this. In fact, one of the advantages of this design here is the fact that you really have a much higher isolation between this pole, this polarized signal, and this polarized signal. So you end up with a really nice cross polarization, as you can see in here. Okay. And let's see what else. The input return loss on the microstrip line were acceptable, below 10 dB. Okay, so that's what we need. Okay, just assuring this one. All right, so one of the things that you're really very important now is the return loss on the what we just showed in here. This return loss here, it becomes very important because this here, and I had this put this on a Smith chart. These impedances that you can see here, these are what's going to drive the LNA device because we really um, what even though in this case for testing and evaluation purposes I put it to the side of the board using microstrip line, but in actuality these don't go like this. This is exactly what they do. Let me go to a clearer one. So the probe in here goes exactly into an LNA, and the other probe goes into an LNA. So whatever impedance looking in here, that's gonna basically kill or make or save the um, the uh, the overall noise figure of the LNB. So these impedances in here. So what I'm going to do is basically take these two here, these impedances, take them into an S parameter file, and then export them to ADS where I'm designing the low noise amplifier in there because that's what's going to be either that or because they're not exactly 50 ohm. You can see the 50 ohm is right at this point. So right now, you either optimize the impedances of these two ports here to be exactly 50 ohm by various ways of matching in here, or like in my case, I said, no, I'm not going to bother with that. I'm just going to take them as is, okay? And then these will become the source files for the LNA device that I'm using for this LNA gas fit devices. So I take these LNA devices, and then the gamma opt. Basically, I design the gamma opt. I design the impedance that you're seeing here. Transform this to the gamma opt that presents the transistor, makes the transistor behave with the minimum noise figure. Okay. All right, so the other thing I'm going to do is look at the E field. So you look at the E field in here, and let's look at this, and that's where you really have to make sure that the vias are spaced correctly and designed correctly, because you can see in here, in fact, how for instance, how I space these so that the wave is constrained, so it contains all of the radiation. It doesn't go out, nothing goes out. In fact, you can see because in here, the distance in here, there's a little leakage in here. So you can see why it's important that these because same thing for the board at the aperture of the waveguide. You really have to these vias. If you're not careful, the signal is going to leak into the board. Okay, and the same thing in here for the rat mouse. This one I had to work very hard to try to optimize the rat mouse hole, the mouse hole in here. Sorry, that for the signal to exit without any interaction with the microstrip line. Okay, and you can see that right here. Okay, so let me go back and make this like this so you don't see this. So okay, so that's okay. So you can see that right there how it's behaving. You want to make sure that because this here is another waveguide, so you're gonna make sure that the cutoff frequency for this gated this metal gate from the waveguide led onto the board doesn't interact with the microstrip line. And the rule of thumb, of course, you always know 3 times, 4 times, 6 times, whatever works out better for you. All right, so let me put this back to transparent a little bit. And let's do some animation so I can show you the propagation of this. And this is going to take a little bit. So while it's doing that, all right, so let me make sure I cover it until we get that running. We covered this, and I covered this. Okay, so basically the E field until this is done. Okay, there it goes. It's actually running. Interesting. Okay, so you can see now what I'm doing is I'm propagating a signal from this end going, and this is rotating counterclockwise. Okay, so I'm going in, and you can see that the signals are one polarization is getting picked up by this guy in here. Okay, and the other one is going through and to the other pole, the printed pole. So we've got the printed pole and the metallic post print. Okay, and it's working nicely. So you can see how the signal is propagating in here and in here. And you can see, of course, like I told you that, of course, this really has a very nice isolation. I'll show you in a minute why this has much more isolation than the other board. And maybe the other thing, this one in here, because there's only one the short reference is printed. It's really shorter. It's thinner LNB. I'll show you what that means in a minute. So let's go here. This guy in here, so we can see. Okay. Just give you the crossband, the cross view. There's one going in here while the other one is going to the other side. The other side is this one here. You can see this one. And of course, this is a short for the wave. Okay, so let me stop this and go back to this one in here. In here, because this is along the waveguide, and you can see that these are exposed to each other, unlike the other one, which has a mixed. And you can see, if I show you the E field, you can see that, watch this, and look at this. So you can see how the wave is actually, there's a leakage. And that's why this one in here has actually a little less, even though I put in a lot of, has lower performance than this one in here. Okay, you can see that this one it's more rejection, and so You can see that, and that's because they share the board, and there is no house, and that's why in a lot of these designs, of course, when you're designing these, you really have to make sure if you look at these people that did this, you need to make sure that this one, you can see how they put a lot of ground via stitching and compartments. So you really want to make sure that these are, in this case, of course, with this one really here, this is either they turn on either on and off. This is for commercial TV probably. So they're either having on and off. So there is no, it doesn't make sense to talk about isolation between them because they're running a single pole at one, they're sharing the path. But in other, there's other ones where it's completely separate. In there, it's very important that, of course, you can see it here. See this, that how they isolated this from this side. You can see that the isolation is huge between these two in here. And that's really what you want to do. You want to make sure that you're really isolated. So let's animate this and show you that how the signal is actually leaking. Even though I put a whole bunch of via a wall line in here and also in here. I'll show it to you in a minute. Uh, this is gonna take a little bit to run. Okay, so it should be running. Okay, so until it finishes, now this is probably, I may have one more part and that's it in this series. So we're almost done. We've done all of them. Okay, there it is. You can see that the signal, how it's actually crossing between each other. And you can see that both polarization, the vertical and horizontal, are not completely isolated in this case because of this issue. Okay. And that's one of the trade-offs. In fact, if you look at these here, these classes, you can see there's a whole bunch of trade-offs between them. I mean, uh, for instance, this one here, if you use a septum, it uses a mechanical part. It's more work to assemble these, okay? And if you use this, for instance, it becomes bulky because you have to transform the circle we've got into rectangular. Many things. We realize this one in here, you can see how close they are. So the cross polarization of this is not the same as would be on this case. And in this case, of course, you can see that because one pole in here and one pole in here, and in the middle there is the metal post that reflects that acts um, as a short back end for this one in here. This is longer than this one here, where this one, of course, because the back end short for the vertical is exactly as the same at the same point mechanically where the other pole is, okay? And you can see that in here, for instance. You can see that, of course, we had the short uh, back. Okay, okay, I implemented in copper, I guess. Okay, there's the metal post, and in here you can see that it has to be at a certain distance between these, and the board gets forced to be larger than this board in here, the other board, than this one here, because this one in here is still running. This one in here, the short, the back short for this polarization is exactly the same plane as the location as the other pole. So it becomes, this one actually becomes a shorter one. Okay, ladies and gentlemen, so this is it. We've covered today one more variety of the LNB to antenna feed structures. With this, I conclude most of these ones. Next, I will go on another topic. You will get announcement on it. So please, again, if you don't mind, please sign on to my channel, go subscribe and share these videos if you can, please. That would help me. Okay, again, this is Dr. Mohamed Nezami coming to you from Jerash, Jordan. I thank you again for viewing my videos, and I hope you enjoy them. If you have any interest in any issues that has to do with these things, please write me in the comments. I will definitely utilize that as a reason to create a video on it. And that way you can benefit yourself from it and spread the knowledge to others as well. Thank you very much and have a great day. Thank you.